Hello everyone. So today I will discuss counters. Counters is a very important topic in digital logic design. So let us begin. There are two types of counters. One is asynchronous and other is synchronous. Now let us understand what they mean. We see that there is a clock pulse here. In asynchronous counter, we have initially given the clock pulse to the first flip-flop. Now for this second flip-flop, the output of the first flip-flop will act as a clock, as we can see here. The modulus number of any counter is given by 2 to the power of n, where n is the number of bits. For example, if it's a 3-bit counter, my modulus number will be 2 to the power of 3, which is 8. So it's a mod 8 counter. Maximum value of the counter is given by 2 power n minus 1. So in case of a mod 8 counter, the range will be from 0 to 7. Next comes the synchronous counter. Now here the major difference we see is the clock pulse. Here to each and every flip-flop, I am simultaneously applying the clock, unlike in the asynchronous case. In asynchronous case, I have to wait for the first flip-flop to give an output. But here, at the same time, each and every flip-flop is getting the clock. Now, there are many types of asynchronous counters: ring, Johnson, serial, parallel. I will discuss one by one daily. Now, let me give you an example for a better understanding. So the question is, design a synchronous counter to produce the following sequence: 0, 1, 2, 3 and 0 back again. So let us start by making a truth table first, which contains of the present state, which has 2 bits, QA, QB, the net state, QA plus and QB plus, and we require 2 flip-flops here. And I will use JK flip-flop. So JA, KA and JB, KB. Now, since it's a 2-bit counter, maximum number of my modulus number is 4. So as we can see, 0, 1, 2, 3. And since it's a 2-bit counter, we require minimum 2 flip-flops. So that's why 2 I am using. And that too JK flip-flop. Now, initially let's see only this part of the truth table. Now, when it is 0, according to the sequence, my net state should be 1. So 0, 0 to 0, 1. Same way, when it's 1, it should be 2. So 0, 1 as 1, 0. And when it's 2, it should be 3 and so on. So this is my sequence. Now, based on this, I have to fill my JK flip-flop table. For that, I would like to show you the excitation table of JK flip-flop. So, when my initial state is 0 and final is also 0, my J and K values will be 0 and don't care. That is because we know in a JK flip-flop, we get 0 in 2 cases. In this case, since our initial state is also 0 and final is also 0, which means there is no change. Whenever there is no change, j and k values are 0, 0. Another possibility of getting the net state as 0 is when my j and k values are 0, 1. So when my j and k values are 0, 1, my output is also 0, 1. Output, which means the net state is also 0, 1. So here again I have the value as 0. So based on this we can say 0 and don't care. Same way, when it is 0, 1, my jk values are 1, don't care. Because since it's changing from 0 to 1, my 1 value should be, j and k value should be 1, 1. That is the toggle state. And the other possibility is when the values are 1, 0, my output is also 1, 0. So we can see it is 1, don't care. So 1, don't care. Same way, 1, 0 will be don't care 1 and 1, 1 will be don't care 0. So if you know this, it will be very easy to fill the truth table. So based on this, since QA is 0 and QA plus is also 0, so when we know it is 0, 0, my j and k values are 0, don't care. So I will just fill 0, don't care here. Same way, QA is 0, QA plus is 1. So when we know it is 0, 1, my values are 1, don't care. So similarly, based on the excitation table, I will fill my entire truth table. So whatever I did for A, I will do for B also. So here initially 0, 1. So we know 0, 1 means 1, don't care. So JB, KB will be 1, don't care. Now next step is to draw the K maps for each and every thing. So I will start with drawing it for JA. In JA we see that there is 1 at 0, 1 only and rest all are don't cares. So this is how my K map will look. Now since it's a don't care, I can assume it to be anything. So here I will assume it to be 1 for the convenience of grouping. So now my value for JA will be QB. Same way, next I will draw the K map for JB. So when we simplify, we see that there are 2 don't care conditions and 2 ones. So in order to make it a quad, I'll assume both my don't cares to be as 1 and JB will be 1. Next, we will draw the K map for KA. Now according to the table, KA is 1 only at 1, 1. So K is 1 only at 1, 1 and there are 2 don't cares and 1, 0. So here again I will assume the don't care to be 1 and I will group it. So Ka will also be QB. Same way I will draw the K map for KB. And after simplifying, we see that KB is equal to 1. Now we know the simplified value of JA, KA, JB, KB in terms of QA, QB and 1s. So now we can proceed to draw the final circuit. Since it's a synchronous counter, my first step should be to give the same clock. So that is the first step. Now from the K map we found out that KA is QB and JA is also QB. So I will assign both KA and JA as QB. So the arrow will go like this. Next we found out that JB is 1 and KB is also 1. So both of them are 1. So I will give the value of 1 to both JB and KB. So this is how my final counter will look. Tomorrow I will be discussing more examples and different types of counters. So please comment in the comment section below and like and share. Thank you.